Hey guys, what's up? Eddie Aho here with KISSanalog.com. Today what I want to do is I want to look at this efficient power conversion amplifier again, this Class D amplifier. And today what I want to do is show you the feedback loop. Okay, the feedback path is really interesting because it helps create this Class D action, this switching action, which makes this unique in the, where a Class A or Class AB has a feedback loop that's, negative feedback, and it's an analog signal that gets summed with, we kind of know how that works, right? Well, the Class D in this particular design is really cool how they've done this. So let me just show you. This is the schematic that I used in the last video, and I kind of changed some. It used to be all red, so the blue is the new stuff. And I drew it so that I could get the output circuit kind of in here. Some of it I just put as a block, as a driver paths. So this is a full bridge output. We got half bridge here, and with tie our speakers to the, one to this part of the half bridge and the other one to this guy. So it'd be a bridged output, okay? And we have an LC filter on these outputs which smooths off all that chopping high frequency Class D action. Well, the feedback is picked up before that. It's right here on the chopping side where these transistors are turning on and off pretty quickly. 400 kilohertz, okay, which is well above the audio range, the say 20 kilohertz, okay. And we put a 1 kilohertz signal and we kind of watched it kind of go through here. So let's just kind of go through that just to talk about this guy. But we strip off the DC, we go through an inversion, another inversion. This is our gain where we have our volume adjust. So we've got 180, 180, we're back to 360, and then we go through a plus, we're still plus, and then we go through another inversion, and this is where the feedback comes in. So where the feedback comes in, it's inverted. And then it goes through another inversion on this zero detect. So then we're back to a plus. So the plus signal here is plus here, okay? Well, imagine the 1 kilohertz coming through and it's climbing. It's going from 0 up to the peak of the waveform, and as it does, it comes through and hits the zero detect, turns it on, and so it turns on this transistor and pulls it up. So you get a really fast rising edge, and it starts your first square wave. Well, when that happens, it drops down into this RC filter in this feedback, and so the capacitor's at the bottom, so it's floating off the ground. But it sent over to this amplifier, and it sees a 100 kilo ohm resistor, pretty high value, and then a 7.5K, which is kind of a small value, and that's the feedback resistor, and the gain is the feedback resistor divided by the input resistor. And since it's a negative sign, it'll have a negative sign on it. Well, if this was 10K, the math would be easy. It'd be, basically a tenth of the signal. Whatever's here, you'll get a tenth of the signal. Since it's a little bit smaller than 10K, it'll be a little bit less than 10K. And it'll be negative. So that plus square wave here hits this, and this will go minus. So that makes our negative feedback. Well, then that goes through an 18K, and our signal's gone through a 15K to come to the same point, which is the summing junction. Okay, and then this amplifier here will sum those signals together, and it's got a 750K, and in comparison to these values, so that's quite a bit of gain. So you get a bunch of gain here going into the zero detect. And this guy here, as it does that, and we're going to minus signal here, it's going to change the zero detect, and it's going to tell it to go negative. So it's going to tell this guy to go off. Well, our signal is still coming up positive, our slow moving 1 kilohertz signal. And this guy's switch, and then it comes around and it's going to tell it to switch again, and it's going to keep on doing that 400,000 times a second versus our 20,000 or versus our 1,000 times a second from our 1 kilohertz. So this guy, the 1 kilohertz is modulating this high frequency filter up and down. So the 1 kilohertz is just kind of riding up and down like this, and we're creating this high frequency circuit here. Okay, so this feedback is really different than maybe what you'd think of in a Class A or Class B amplifier. So what we're going to do is we're going to look at I'm going to bring you over here. we're going to look at the scope, and I'm going to show you the input to the feedback, and then I'm going to show you the output of the feedback amplifier, and you're going to see this integration circuit. See, there's an integrator, there's a capacitor here, so it doesn't automatically go square wave here. It has to charge this cap, so it's going to be like a cap charging circuit, you know, so you're going to see kind of a shark tooth waveform coming off here, okay? Well, then look at this. We've got another integrator up here. So by the time this shark toothy guy goes to another integrator, it's going to look sinusoidal. And this time constant here is going to help set up this 400 kilohertz signal. This what's going to look like a sine wave. And as that sine wave, 400 kilohertz, is riding on top of this 1 kilohertz, you know, slowly moving like this. We got this really fast thing. Well, this fast moving 400 kilohertz, it's not always centered evenly on top of that 1 kilohertz. Sometimes it's more below the line, and sometimes it's more above the line as it goes through it, okay? And then that helps the zero detect tell what duty cycle to put out. And a wider duty cycle will mean it's still going up, and then it can, when it comes down close to the zero crossing line, the 1 kilohertz signal, duty cycle go closer to 50%. As it goes negative, it'll go, you know, to some smaller duty cycle, okay? So it'll be max, top, minimum at the bottom. Alright, so we'll compare it to our output signal so you can have something to look at, okay? So you can kind of compare what this signal looks like in comparison to the output signal. Alright? Well, let's bring the camera over and get this thing done. I hope this helps. Once you see this, I hope it helps you kind of get a better understanding. It is kind of complex. It's pretty interesting, I think. Even though it's done with a lot of op amps, so it's still discrete in the sense that it's using, you know, op amps. It's not using the big integrated circuit, but it's not using a bunch of transistors and things like that would make it look way more complicated. But, you know, still, what's neat about this particular circuit is because it is discrete, it's not a big integrated circuit, we can see the blocks and how they work. And I think hopefully it's given us a good feel about how Class D works. Okay? So this will be part of the playlist that I've made with all the other videos. And alright, let's do this thing. Okay, so what I'm doing right now is I have two channels. I have channel 1, and that's the yellow one that's flatlined. That'll be the one I'm going to be probing. This green one that's not really locked in, I'm going to be triggering off the channel I'm probing. The green one is the output signal. And so channel 4 is the second signal, and it's 10 volts per, and it's 10.9 volts RMS right now on the output. I have that 8 ohm resistor as my load. Okay, now watch the yellow one, and that is going to be the feedback pin. Okay, there's that 400 kilohertz. So now what I'm going to do is, I'm going to set up the scope. I'm going to set up the scope here, the trigger on it, so that it's in normal mode, and then it's, instead of auto where it just automatically triggers, it's going to trigger whenever it goes past my trigger point, which is right here. So once we put a signal on there, it'll trigger. And the reason I'm doing that is, here, let me zoom back in for you. Alright, and the reason I did that is so now you'll see why. It'll be obvious. I'm probing that signal. Now when I lift the scope up and see it's triggering, when I lift up, it'll stop. That way it'll save me a hand. Okay, now I'm going to reach up and lock it in place, and I'll go ahead and turn down the power supply, just let it run a little cooler. Okay, so now I'm going to hit the zoom button. See those little green bars? That's what's in the window right here. And you see the green waveform? That's our 1 kilohertz sine wave. And right here, this green waveform, it's right at the top. And as I scroll across, here, let me get rid of that. As I scroll across this green waveform, it'll go down and up. It's our 1 kilohertz wave, okay? So, and we can see our square wave here. I'll zoom in just a little bit more so you can see the duty cycle. So you can see the duty cycle, it's mostly on, okay? Now, and the green waveform's up. Okay, now watch as I scroll across. You can kind of see me scrolling here. I'll go slow, and our green waveform's dropping. And when it's in the center of the screen there, where our reference point is, and our trigger's right here, now it looks like 50% duty cycle. Now, as we scroll down, continue scrolling across, I'll go to the bottom of that 1 kilohertz waveform, and now the duty cycle is smaller. Okay, so that is the square wave output. That's our Class D before it gets LC filtered. Okay, so, and that's our feedback right there. So now I'm going to go on the other side of the feedback amplifier. Okay guys, so I changed it to 0.5 volt because it's being divided by 10, or a little bit more than 10, so I changed it to 0.5 millivolt to 0.5 volt instead of 10 volts. And it's auto triggering, so you can see our green waveform, our 1 kilohertz, it's popping up and down here. That little green bar is what we're seeing here, and you're going to see the feedback signal here as soon as I touch it. Here we go. Okay, there we go. Okay, now let me go back to that other triggering method so I can touch it and let go. Okay, there we go. Now I'll freeze it and turn off the power supply again. Alright, so there we go. If you look up here, you see the 1 kilohertz, this green waveform. We're at the top of the waveform again right there. And see this yellow one? It's inverted from the green one, because that feedback amplifier is a negative feedback, right? So, but look at this. See how this charging and discharging? So we did have a square wave, but now look at it. Alright guys, so what I did is I added another channel. Channel 2 is 10 volts. So we're going to look at the feedback, the input, the signal we looked at the first time, the square wave, and then I'll look at the output of that amplifier here so you can see those two signals relative to each other. And then you also see the output, of course, pop up. So let me get both these probes in here. Okay guys, so that's the feedback signal that we just saw. That's the output of the feedback amplifier. Now I'll try to touch the input again. There we go. And now I'll lift up, so hopefully capture it. There we go, we caught it. Okay, so this is our feedback, the blue waveform. Here's our output, the green waveform at the bottom. Okay. Now if I touch channel 4, it'll highlight the green waveform up here. So you see we're almost in the middle of the waveform as it comes down. And the green's almost there. I'm going to just bring it so we can bring the green right up to the middle of the screen. And that'll be, that's virtually ground right there. Okay, there we are. And duty cycle looks like 50%. That's our feedback. See, it's 10 volts per. So I have a little over 20 volts coming in, so we can see the plus minus 20 volts. And it's 50% duty cycle. And look at the output of that integrated op amp. So when it's 50% duty cycle, this is an interesting thing. The amount of energy on the plus half is the same as the bottom half, so this yellow waveform is in the center of the screen. But now as I go along our green waveform, our input waveform, I'll go down to the bottom. See, our green is down at the bottom. So now look at this. The yellow waveform, the blue one, the duty cycle has changed, so it's less time on top, more time on bottom. And now look how, but it's inverted, right? So the yellow one is now more hot, it's above the center line more often. So you see how the yellow one's starting to go up and down with the green one? It's going away from the green one. So that's our negative feedback. And you can see how it charges up, and this thing changes, and then it discharges, this guy changes. Okay, so now let's go look at our signal coming in compared to this guy, the yellow one. So I'm going to change this blue one to a lower value, I'm going to go about a half a volt too. I'm not sure what the input signal is going to look like, so we'll have both half a volt now. Okay, let's do that again. Okay, so I'm going to take the yellow channel and put it on the output of the feedback amplifier, and the other probe will be on the output of that buffer amplifier where our 1 kilohertz signal is coming in. Okay, there they are. See if I can lift this probe and capture it. Okay, cool. Alright, I think I froze it there. Okay, now see the blue one? That is the AC signal coming in on the buffer. The green one, it's following the green one almost perfectly. Let me get a few more cycles in there. You can kind of see the green and blue one. There we go. They're in phase with each other. Now the green one is our output, 10 volts per division. And the output of that buffer, our signal going through the signal path, it's 500 millivolts per division. Okay, and then this guy here, our feedback that's coming out of the feedback amplifier, see how it's inverted, and it's that 400 kilohertz clock. So this blue one and the yellow one are going to be summed together in the next amplifier. So let's go look at the output of that. And what I'll do is I'll use this yellow one again as a reference. This will be the output of our feedback amplifier. We'll compare that to the output of the summing amplifier. Okay guys, I'm on the output of the feedback amplifier, and I'm going to try and very carefully go to the output of the summing amplifier. Okay, there's the output of the summing amplifier. Okay, I'm going to lift the lead real quick, try to capture it. Okay, cool. Stop triggering, but I'm going to freeze it anyway. You kind of see up here where it stopped capturing the yellow one, where I lifted it, and it just caught all this other information. But, alright, so that's pretty cool. Now, let's bring our cursors, bring this green waveform up towards the top of a waveform. Probably right about there. It's the top of that waveform. See how high the green one is? And look how low the blue and yellow one are. I turned up the amplitude of the amplifier a little bit, and that's really heating up my resistor. I'm going to turn off the power supply. But anyway, so you can see that these waveforms are mostly below the 0 line, so you get a very short duty cycle. And look at this shark tooth waveform, how it's changed. Okay, let's go towards the middle of the waveform. We're bringing the green in the middle of the screen. A little bit tricky. Alright, that's pretty close, sorry. Over here it looks pretty close, but see how it's mostly in the middle of the waveform right here, the blue and yellow one? They're 50% duty cycle right in the center of the screen where the green waveform is just crossing, and then it's starting to go up again. So let's go to the bottom of the waveform. So the green's all the way down here, and see how these guys, the little peaky thing here, so that's how we control the duty cycle and the Class D action, creating this sine wave that rides on top of our 1 kilohertz. So that's how that feedback, feeding back that chopped up square wave, is converted to basically a sine wave that rides on top of our audio signal, creating the chopping and the duty cycle. I had to do this with too many hands, so I had to turn over the board and carefully probe. This is the output of the 0D tech circuit, and there's some noise on it. It's switching, but really the only thing that matters are these square waves, because that's what's going to make those output transistors drive. So the noise will be ignored. But let me just scroll through that. You can see our green waveform here at the bottom. I'll go towards the middle of the screen. Right, whoa, just over. Okay, right there's about middle. And you can see the output's about 50% duty cycle. Now you see how it's floating above ground now, it's going to go through a capacitor, and on the other side of the capacitor it'll be referenced to the output return. So right now it's only duty cycle is the only thing that really matters, and we'll go towards the top of the waveform, bring the green up to the top of the screen. See how wide the duty cycle is? And then we'll bring it down to the bottom. See the green's down here? And look how narrow the duty cycle is. Alright, so that's how the feedback affects how the duty cycle and the 400 kilohertz is generated. Alright guys, what'd you think of that? I think I'm finally done, unless somebody comments real quick, because I'll post this tonight, I think. Well, I'll try. I'll post it tomorrow probably. But let me know, and if there's something really important, maybe I can keep it and do another video. But otherwise, I got a lot of other stuff to do, and we've got to move on. So, but let me know what you think. And I want to thank EPC for letting me borrow this for all this time. That's awesome. And it's been fun. But alright guys, let me know your comments, questions, and I want to thank Richard for the question about how the feedback works and why the pickup point is where it is. I thought, yeah, you know, I really should do another video showing just the feedback loop, because it's probably the most complex part of the whole thing. So alright guys, thanks a lot. Thanks Patreons, thanks everybody for watching. I appreciate all your support, and we'll see you next time.